opportunity. Thanks very much. Thank you. You know, I have to say, I always enjoyed being on this campus. And I've been here on campus many times, going back to when Dale Compton was a member of the IE department. But I can't tell you what an honor it is for me today to be here as a Neil Armstrong professor. You know, I never met Neil Armstrong. But like hundreds of millions of people around the world, I watched Neil Armstrong step off the lunar module on July 20th, 1969. I think that's the right date. And you know, it was absolutely stunning. You know, to think that a man like Neil Armstrong and then Buzz Aldrin, who followed him, would have such trust in our science and technology that they would be willing to fly to the moon, get on the moon, step down onto the moon, and then had the faith that they would get back to the Earth safely. And they did, of course. And I'll tell you, I never felt more personally proud. Now, I was very young at that point. This is 1969. Most of you guys are probably not even born, right? How many of you were, you couldn't possibly have been born in 1960? Look at these kids. But you know, the interesting thing was that these folks had such incredible trust in our technology, and it was deserved. And frankly, as a young engineer, I felt very proud of being an engineer at that point. I really did. Of course, I still do, but I mean, that was a moment in history that, you know, you just do not forget those moments. Now, I said I never met Neil, and I never have met him, never had met him. But I did work with astronauts during my career. When I was at MIT, I directed a center called the Materials Processing Center. And you might remember that on Skylab and Space Lab, there were experiments done in microgravity conditions to grow large silicon, perfect silicon semiconductor single crystal ingots, really large. And protein crystals and other materials in a microgravity environment, which added some interesting characteristics. So when I was director of MPC, Materials Processing Center, I used to go with some of my colleagues to Huntsville, to the Marshall Space Flight Center, and we'd work with the astronauts who were preparing the experiments. And it was really thrilling. I mean, these guys were, you know, I think of people who are brave, and the Navy SEALs always come first into my mind. But I don't know whether SEALs are more brave than astronauts or not, but the level of excitement that you see in the astronaut corps and in the Navy SEALs is just truly remarkable. But I enjoyed that enormously. So I have worked with astronauts. I actually know the astronaut who was the second last person to walk on the moon, Jack Schmitt. It turns out that, well, his name is Harrison, but they call him Jack. I'm not sure why, but he's Jack Schmitt to me. I met him when I was in Washington on sabbatical. I was an advisor to the House of Representatives Committee on Science and Technology. And at that point, Jack he flew on Apollo 17, landed on the moon, walked on the moon with Gene Cernan, I think. Cernan got on this module last to come back to the Earth, so he was the last man to walk on the moon. But Jack Schmitt was there with him, and he was a senator from New Mexico, I think, at that point. We became close. We got to know each other. Close maybe an exaggeration, but we knew each other, worked together a little bit, and he came to MIT a couple of times to visit, and it was great. So I feel a special, honor in being named an Armstrong professor. I really do. And I can't thank you enough, the folks at Purdue, for giving me that opportunity. So I'm delighted to be here today. I'm gonna talk to you about something that is very close to my interest, and that is a program called, let me get my pointer here, or my control. I'm going to talk about what's called the Materials Genome Initiative. And I'm going to give you, a 30,000, well, maybe I should say a 389,000 mile view of this. because it's a very broad program. It began actually in 2011, grew out of the Obama White House and the Office of Science and Technology Policy, which had a vision of being able to use computational tools to accelerate the pace at which advanced materials are discovered, developed, and transitioned into manufactured products. Now, I'm not a computational material scientist, not a practitioner, but I have had a long-standing interest in advanced materials. This goes back to Chandy mentioned that I worked for Martin Marietta Corporation at one point. When I worked in their research center, but the research center had interaction with the division in Denver that built Titan launch vehicles. Martin at Marietta at that point was involved in building ICBMs and defense weapon systems. And the labs had some association with all of that activity. Along the way, I've had interest in things like hypersonic vehicles. You know, we have a Space Force, or we're building a Space Force, and that's going to require some new materials in order to meet the demands of hypersonic flight. And so I've had interest in advanced materials for a very, very long time, but the usual approach to developing advanced materials is trial and error. You thought this might be a good material, you made some adjustments, you tried it, and if it worked good. If it didn't, try it again. But MGI it's computationally derived, and this is a description right in here. This is the idea. Using computational and experimental tools, and depending heavily on data. Data is a cornerstone of MGI because you're developing models, you're introducing what's called combinatorial synthesis in order to create a whole host of materials that may be good candidates for whatever application you're interested in. And then you're using experimental techniques and sometimes computationally aided to screen those materials in terms of their final application. So I'll tell you more about this as we go along, but that's essentially the approach. The whole idea is to serve human welfare, is to, for example, to look at the issues of clean energy, to look at the next generation workforce. You know, when you look at this, in order to make this really work, you've got to have a workforce that understands how to use this model. I'm going to tell you more about the model in a moment. But you've got to have that, and then of course you need to look at national security. So the whole vision here is to be able to develop new materials that meet a demand that is either addressing national security interests or social interests, and to be able to develop that material much faster than in a conventional trial and error approach, and likewise at a much reduced cost. That's the whole vision of all of this. That's the point. There are many different federal agencies involved with MGI. You'll notice NSF. Let's see. NSF is one of them, a major player. Why is NSF important? They in fact are important because they provide resources to PIs who are typically university faculty. At universities, there are students who are part of the programs that are sponsored by NSF, and those students represent the intellectual infrastructure for the evolution of MGI. So it's an important part of this. And then you also see NIST. Why is NIST important? Well, as I mentioned, this is all computation. This is data mining at a very high level. The data has to be verifiable. It has to be properly managed and provided, made accessible to researchers. And that's where NIST comes into the picture. They're vital to this whole operation. Many of the other agencies are actually users. The Air Force, for example, they're involved in developing hypersonic vehicles. So at some point, they're going to need to deal with the fact that in order to fuel a hypersonic vehicle, you're probably going to use hydrogen, and you've got to make it lightweight, so you're probably going to need a high-strength material. And most high-strength materials are embrittled by hydrogen. So you need a new material. You need some material that is more resistant to hydrogen than what is commercially available today. That's where MGI comes into the picture. In those kinds of situations, you have a demand, you describe the demand, and then you figure out, using computational material science and engineering, how to create that material. That's the whole idea. There are some agencies up here that I'd never seen before. Who knows what this is? NITRD. You ever see that one before? That was new to me. It's Networking and Information Technology R&D. I never saw that before until I looked at this slide. But so you have a combination here of organizations that are federally sponsored, by and large. And here's the important point about NSF. NSF, DEMREF. This is an interesting room. I can actually stand here and look straight ahead and read what's on the screen off this. So I'm going to do that. NSF has developed a program called Designing Materials to, let's see, what does our DEMREF stand for? Let's go back a bit. Designing Materials to Revolutionize and Engineer Our Future. That's what DEMREF stands for. The government loves acronyms. They're sometimes hard to remember, even for me. But that's what it stands for. So the DEMREF program has been, it is, in fact, the primary program in which NSF participates in MGI. And the aim, as I said, is to discover and develop new materials essentially by developing fundamentally based models, by designing and making materials to meet a specific and desired functional demand, and to do this from first principles. So it's no longer trial and error, it's from first principles. But the interesting point is that, DEMREF is on this end of this is called a technology readiness level diagram. This from discovery of material all the way to deployment. And MGI is all about deployment. It's not just about discovery. This isn't a program that is intended to provide a research opportunity without some endpoint being met. The whole goal and the aim of MGI is the deployment of new materials. That's the whole goal. So NSF is largely on the early end of the technology readiness level diagram. It's involved with fundamental research. It's involved with developing experimental tools, developing computational tools. It's involved with students and PIs at universities, which represent, as I said, the workforce. But the whole goal is to go out beyond that. And I just want to make the point that at this university, you have some DEMREF sponsored programs. And in fact, Hyan and Ollie are here today, and at the end, later on in this program, they're going to talk about some work that's being done under the auspices of DEMREF right here on campus. In the last cycle, when DEMREF awards were made in 2023, there were 4 new projects begun here on the Purdue campus. Hyan is involved with this one, but you see there are others, 3 others on this list. And I don't know how many in total there are on campus, but I know there are more than 5, because Ollie is involved with the project that began a few years back. So DEMREF is a part of your environment. You may not have known it, but it is, and it's an important part. So I mentioned that MGI began in 2011. DEMREF started shortly after that, maybe a year later. And in 2021, the National Science Foundation asked the national academies to conduct a study to evaluate how well DEMREF was actually meeting the goals of MGI. To evaluate the DEMREF goals, its progress, its scientific accomplishments, but all with the vision of serving the nation's vision for the Materials Genome Initiative. So they set up a committee. And as I've mentioned, let me show you the committee. Whoops. This is counterintuitive, I got to say. This is the committee that was established. I was a co-chair. My co-chair, Karen Rabe at Rutgers, is a solid-state physicist. She is a practitioner. She's a computational materials, solid-state materials practitioner. She's very, very good. And I think she and I represented a pretty good combination. I had an intense and long-standing interest in advanced materials. She had an interest in developing new materials based on computational material science and engineering. But we had an outstanding cast of characters in our committee. Some of these names you may, I keep hitting the wrong buttons here. Some of these names you will likely recognize. For example, I know Hayal recognizes and knows Ray at Texas A&M. Gerd Cedar, some of you may know him. Gerd Cedar, he was at MIT on the faculty when I was at MIT. And just to make an important point here, I think it was around the late 1990s, Gerd Cedar and a guy named Yet-Ming Chang and Don Sadoway, three of my faculty colleagues at MIT, were looking at lithium-ion batteries. This is before they became commercial. And they were struggling with the idea of, well, we need a cathode material for these lithium-ion batteries. We can't find a good, durable cathode. What should we use? And I'll never forget this. I remember Gerd Cedar saying, look, I think I can develop one based on first principles. And he said, let me take a shot at this. And he said, we left the conversation. A couple of months later, he came back and he said, I know what we need to use. Let's do some experiments. And he did. And it worked. Yet-Ming Chang went on to found a company called A123, the lithium-ion battery manufacturer. Don Sadoway has been involved in all sorts of technologies related to green steel making and green cement making, which may sound contradictory, but the fact is you can produce steel using low-temperature electrochemistry if you're smart about it. Oops.
Unknown caller.
Oops. Sorry about that. I should have turned this off before I started, right? One time I was giving a talk in a National Academy meeting, and my wife and I have an agreement. If she calls me, whenever it is, I answer. And I'm standing before this group of academicians down in Washington. My phone rings, and I look at it. It's my wife. So I said, all right, I have to answer this. Sorry. But this is not my wife, so I don't have to answer it. Anyway, these guys are, Gerd Cedar's now at Berkeley. Don Sadoway and Yet-Ming Chang are both at MIT. But they're really serial entrepreneurs, and they really understand how to take new materials and put them into service. And that's what this is about. That's what MGI is all about. Developing new materials, finding a way to getting them into service, and making a difference. And by making a difference, I mean not just with a profit motive, but really serving a social purpose. Social purpose or a national priority, like national defense. That's what this is about. But in addition, there are other people. It's a very good mix of people who are, for example, Feliciano is a high-performance computational expert. Ahmed he's a jack of all trades, but a really brilliant man. He's at the University of New York in Buffalo. David Green is a polymer chemist. Preeti is at Exxon, she's a chemical engineer at Exxon. Bob Cohn is a mathematician. We've got a lot of different disciplines covered in this committee, and it was really a wonderful committee to work with. The interesting fallout of all of this is all of this happened during COVID years. We didn't meet once in person. All of our meetings were virtual. But that was actually, it's a strange thing to say, but if there's anything positive about COVID, it was the evolution of virtual meetings, because we could meet with people in Germany and in South America and in Asia virtually in order to get information for our study. We couldn't have done that in a typical National Academy studies, which are done in person. That would have been just about impossible. But you'll see the consequence of that in a few moments. Well, let's see. I've got to hit the right button. There we go. So here's what we're asked to do. As I said, to evaluate the goals, progress, scientific accomplishments, importantly, to provide high-level strategic recommendations. You're going to hear a lot about this. And to address effectiveness based on making sure this is not just metals, not just ceramics, but the breadth of materials, including biological materials, biomaterials. To look at different NSF components and to make sure they're incorporated in some fashion. To respond to new opportunities in data sciences, including artificial intelligence. Accelerate the fundamental research towards eventual deployment and manufacturing, and to attract and develop an innovative and diverse talent pool. I just want to say a word about AI at this moment. This was an interesting conversation in our committee. AI is double-edged. It's a double-edged sword. This may be a case, MGI, where AI can really show its value. But one of my colleagues at Exponent, early on, decided he was going to try to use ChatGPT when he was writing a technical report. He was going to use ChatGPT to get some references on the technology that was relevant to the report. He asked ChatGPT for some references. He got back about a dozen references. They referred to journals that were well known. They looked very authoritative. Not one of them was legitimate. They were all fake, every one. And shortly after that experience, there was this attorney in New York who filed a brief with the court that included some case histories generated by AI, by ChatGPT, by generative AI. Every one of those cases was a fabrication. So, you have to, if you're going to use artificial intelligence, you've got to make sure you've got verifiable data. You've got to make sure you're using it properly. And you have to be conscious of the fact that it can be misleading. But I think MGI may be one of those situations in our technology where artificial intelligence may truly be useful. And that we'll see. We'll come to some of this. I'm going to give you, in this 380,000 mile overview, I'm going to give you just a little bit of a look at the outline of the report that followed. And I'm going to give you a link to this so you can read it at your own leisure if you choose. But I wanted to point to one thing that's important, and that is, whoops, keep doing that. I wanted to point out this chapter, Counterparts Around the World. I've mentioned that in 1990, in the late 1990s, that Sadoway and Yepming Chang and Gerhard Sader were doing computational material science and engineering at MIT. It was on a pretty local basis. And there were other people in other parts of the world doing similar things. But in 2011, when MGI came along, it catalyzed something like a condensation process among researchers who are doing these things in various countries. And so today you'll find that MGI has catalyzed similar organizations in Germany. Nomad is also in Germany. There's a Canadian equivalent, an Indian equivalent, China, Central America. There are MG-like offspring now all over the world. So this is not just a matter of the White House and the United States doing something for the American economy. This can affect the economy of the world. And it can affect the technology of the world, in I think a very useful way. So before I show you more, I'm going to just tell you what the overall view is, and then I'm going to show you some of the detail. The overall view is that NSF is the MGI partner that through this program called DEMREF, designing materials that revolutionize our engineering future. DEMREF developed the fundamental science, the tools, and the workforce that enable industry and other government agencies to develop and deploy new materials. And deployment is the final goal, remember that. Going forward, what I'm going to show you in a moment is that these activities should begin, we want DEMREF, as it matures, to position itself to reach the ultimate goal of cheaper, faster, new materials that meet national priorities by deliberately engaging industry and federal agencies. When I showed you that list of 18 different federal agencies, you may have said, well, there are no corporate entities listed. That's, when you think about that, why is corporate America, why is corporate Universal not involved in this? Well, I think there's a good explanation for that. What we're talking about here is actually what we've been doing in education for decades, for centuries. we teach people how to leave the university and go out and serve a useful role. And if we're teaching them how to use computational tools and they go off to industry and use those tools in industry to develop a new product that serves either a national priority or meets a social need, then that's a success story. But it in fact is the government. In almost every one of these national enterprises that I mentioned, in Germany and China and South America, they're almost all driven by the governments of those countries, not by industry. But industry is the beneficiary. And industry is actually a proprietary beneficiary. So there are some potential conflicts, because if people go off and start working in this industry using MGI techniques, they're going to develop products, they're going to develop software, they're going to develop tools. Are those now corporate entities that, it's a matter of private funding versus public funding, isn't it? And they have a right to their work. But that's always been the case. When I took courses in physical metallurgy way back when I was a student, what I put into practice at Martin Marietta didn't carry any proprietariness. It's what I learned, what I put into practice. And I think the same is true of MGI. It just happens that most of the support for MGI today is federal support. I'm not going to go through these in details. I got 4 slides with these, but I want to hit on a couple of points. First of all, oops, I keep hitting the wrong button. And I did it again. First of all, I think I need one more, don't I? Yeah. I'm still doing it. This is a counterintuitive. Okay. First of all, the third one, 6.3, data. Data is the cornerstone of all of this. It's got to be properly curated. It's got to be verifiable. It's got to be made acceptable. Advances in the fifth one, advances in robotics. I just mentioned AI. I think this may be a case where AI could be really, really helpful. With care, but I think it could be really productive. We really want, suggested very strongly, that DEMREF, I'm looking at the first one, 6.9. Scientists at government agencies they're mission oriented. They know what the national priority is in terms of a defense system. They're building hypersonic vehicles. They know what materials are, what materials needs are. So they should be in a position to really provide guidance to PIs at universities, and that should be helpful in terms of building these systems in a corporate world. So we really want to see this sort of synergy develop. DEMREF is important in terms of the fundamentals that it produces, in terms of tools and theory and so on. But that has to find its way into deployment. The goal of MGI is deployment. That's the key point. Let's see, what else? Let's go. I don't want to spend too much time on this because we're going to get late. This third point, NSF and DEMREF should take a leadership role in developing a national plan for a platform that creates a interoperable system that allows comprehensive collection, dissemination, and use of data. The underwriting thought there that should be implemented by NIST. NIST is the carrier for this. So, but remember, data. Without good data, you get what you expect. Results that you cannot trust, like the ones I mentioned earlier. The review my colleague did of the literature and the filing of a report in court that really wasn't very useful. Let's see, what else do I want to say? This one is important. NSF should create new opportunities for translational funding through supplemental mechanisms. And that could mean something like generating proof of concept contracts. So that if you develop something in your lab here that you think has important potential to meet a national priority or social need, and it has to find its way into the marketplace, you should have an opportunity to demonstrate by proof of concept that it works. NSF today doesn't do that, but we think that's not a bad idea. In fact, we recommend it. There is another aspect, and that is this program called GOLI, Grant Opportunities for Academic Liaison with Industry. These government agencies love acronyms, GOLI. But that's an important one. One of your programs that I had listed that was funded in the 2023 awards from DEMREF is a GOLI program that involves involves the Air Force, and I think I've forgotten which corporate entity, but it's a university, national entity, the Air Force, and a corporate entity. That's important. So I want to just show you a quick sampling of some of the MGI work. One of the things that has interested me, this is work presented by a colleague at Penn State, Ismail Dabo. Some of you, I don't know, some of you may know him. He's working on water splitting using semiconductor photoelectrodes. Now, you could go into a lab this afternoon. If you take a battery and you connect the terminals on the battery to electrodes, you can split water today as long as you've got enough voltage. You can do it this afternoon. But we have a planet which is 70% covered by water, and we have typically a plentiful supply of sunshine. Today would be a beautiful day for water splitting here in West Lafayette. And we should take advantage of that. So how else can you do it? Well, you can use photovoltaics, you can use solar panels, produce EMF using solar collectors, and use that. Or you could use semiconductor photoelectrodes. Here the issue is, and the idea is to use sunlight to generate band gap transitions. Move an electron from the valence band into the conduction band. That creates a hole. The hole can be used to oxidize water to produce oxygen. And the electron can be used to reduce hydrogen ions in water to produce hydrogen. This was actually demonstrated in 1972. The problem is, and this is, let me just skip this one. We can skip this one for the moment. The problem is that these electrodes, many of the early electrodes, for example, those that were examined in the late 70s, were not chemically stable in water. That's a problem. You've got semiconductors that if you put them in water, they will function, but they will also degrade. They're not durable. And so you need not only a semiconductor that has a proper band gap. This is a good illustration, because it shows you that what you're trying to do is use solar absorption. You want the solar spectrum to impinge on these semiconductor photoelectrodes, but they have to have the right band gap. You don't want a band gap that is too large, because if it's too large, it's going to require more of the shortwave infrared radiation rather than the majority of the solar spectrum. So you want to essentially look at all of the possible. You want to basically align bands by choosing elements which you can add to your candidate material to modify the band gap. You want to make sure those components are abundant, that they're synthesizable, can be synthesized, and then you use that to refine the band gap so that it's where you would like it to be. You want it to be pure, because that impurities can affect the band gap, and that will lead to photocatalytic activity. This work was done at Penn State. They were looking at models in which they are planning to use particle semiconductor photoelectrodes, not large-scale objects, but particles. So you actually, by using combinatorial methods, very much like pharmaceutical manufacturers use, you create a whole host of candidate materials into what is called a library. And then you reduce that number using experimental screening techniques, computationally aided. And you end up with a few candidate materials, and you go on from there, and you can tune the bands. You can actually, you've got a handful of materials that end up at the bottom of this trough, and you can use those materials for laboratory testing to see if they work. That's the whole experiment. And we're getting actually very close to having stable, durable, workable semiconductor photoelectrodes. Now, I have one of my favorite visions of all of this is that someday a president of the United States will walk up to a microphone and he'll say, this president will say, I'm announcing today that I'm committing the United States to a hydrogen economy. Water covers 70% of the globe. It's plentiful. Sunlight is plentiful. If we're clever about it, we'll use semiconductor photoelectrodes to split water. This will be an advantage in the sense that water and light are plentiful and available not only to the legacy nations, but to the non-legacy nations all over the world. There are no geopolitical boundaries. We don't have to worry about transporting fuel. They're available locally. And I then have this vision that someone from MGI will stand up and say, Madam President, we will produce that material. Now, there are two objects there, two unknowns. One is that you have to make sure you can find a stable, durable photoelectrode, but the second is that you have a woman president. Now, the reason I'm so positive about that is that I have 4 granddaughters, and I have very great hopes for these kids and their generation. So I'm looking for a woman president out of their generation. That's my grand vision for semiconductor photoelectrodes. Just a couple more examples. This is work done in 2010. Again, before the MGI project began. This was done by a company called Questech. Some of you may have heard of Questech, but if not, they developed, landing gear on airplanes. This is military aircraft, but landing gear on whether they're commercial or military aircraft have to be high strength. You want high strength, low volume materials. But the high strength steels that have been typical and have been used for decades are subject to hydrogen embrittlement. Well, this organization, through this combinatorial approach that I've mentioned, they developed a new material that is now used on military aircraft routinely. And it works. It's a beautiful demonstration. And this was all developed by doing essentially a combinatorial analysis and approach to finding a material that was suitable. Here's another example, again by the same company. This is the name of the company, Questech. They developed what are called hook shanks for military aircraft when they land on a carrier. You land on a carrier, you've got to stop before you go off the other side of the carrier. And those materials have been a problem for a long time. But this is a new generation. It's a Questech alloy called M54. But it's just another demonstration of a computational material science and engineering generated material that's put into commercial use. If you have an Apple Watch, mine would not apply here, but if you have one that's gold, or if you have one that's anodized aluminum, the chances are this was developed by Questech, the materials of construction. And I mention this again because there are some important people here. You'll see the name Olson. This is Greg Olson, was a colleague of mine at MIT. He left MIT, became a faculty member at Northwestern, founded this company called Questech way before MGI began. But it's a very important player in this field today, commercially. And in fact, it's found its way into, one more illustration. It's found its way into Tesla and SpaceX because one of Greg Olson's students is a guy named Charles Kuhlman, and I keep hitting the wrong buttons. Charles is a vice president for materials development at Tesla and SpaceX. So he's carrying the flag and the concept into practical applications. Now, I do want to show this slide because I'm going to ask 2 of your colleagues to join me. Haiyan first. As I mentioned, Haiyan was awarded a DEMREF contract in 2023, so she's about 6 months into it. Ali, on the other hand, has had a DEMREF contract for about 3 years?
4.
Almost 4 years, okay. And I wanted you to hear what's going on in this campus that has to do with MGI and DEMREF. So we're going to have just a few comments on it.
Yeah,
Hi.
thank you, Ronald.
Oh, you're going to need a microphone.
Oh, I don't think
think so. I can speak very
No, you're going to need this. You're going to need this.
Okay.
Otherwise, we won't be able to hear you. Yeah.
I can.
Oh, this is complicated, isn't it? Here you go.
Okay, great.
Great.
Yeah, thank you. Okay, I will hold this now. Okay, so great. Thank you, Ron. So my name is Haiyan Wang from MSc. I know many of the folks from IE, and actually we work on material integration. So I try to understand how this works. Okay, I'm backwards. Okay, so I prepared the 2 slides to highlight what we have been doing. So we got the project awarded last October. Joining me was Edwin Garcia from MSc working on phase field modeling, Peter Bermel from ECE, and Minhao Qi from ECE working on device modeling and integration. So basic idea is using vertical line nanocomposite structure. Instead of using one material, we try to couple multiple materials together. Really echoed with the DMR-EF idea is to do a material design which cannot be done by conventional material exploration method. So we try to design the material in a very unique way by adding A and B together for optical design. So I will show you a few examples. Well, we can make a variety of nanocomposite structure using very dissimilar material, metal in oxides or nitride in oxides, to integrate very dissimilar interface material together and try to make unique optical components so that they behave very differently from the single material alone. But for doing that, there's a lot of complexity. Well, we have to do in-plane design or ordering of the structure because those are all done by basically self-assembly process during thin film growth. On the other side, there's a lot of interesting work talking about strain between the interface of the 2 material and also the integration about the devices. I think Ron discussed at the end, we hope to integrate this new material onto a device platform. Potentially that can be used for maybe unique waveguide structure or maybe even optical sensors. So I also put in some scope, basically to echo with Ron's discussion on material genome initiative. There is a loop between us while I make the material, and I do a variety of electrical, optical, and magnetic property tests because the idea is really, hopefully some of the magnetic component, the optical component, and also the piezoelectric framework all interact with each other in a way. So I have to do a whole bunch of tests at the material platform. Now I send the material to Minhao. Actually, Minhao will be doing the devices and integrate on his waveguide structure and test our material. And Peter Bermel will help us to do actually optical simulation on the design. And Edwin Garcia actually helped me on the phase diagram calculation as well as the nanocomposite design platform. So the goal or the idea is really by doing the nanocomposite design using the vertical structure, hopefully we can design material that typically cannot be achieved by single material alone. So here I'm plotting a dielectric function in perpendicular and lateral direction. And most of the material comfortably lie in the 45-degree angle, which is very isotropic. So in order to achieve design means you want to get certain kinds of dielectric response in certain angle or certain direction. You really need to design your material in a way and possibly to make either type 1 or type 2, those are called type 1 or type 2 hyperbolic structures. And so that you can really say, okay, for a certain optical component, I need a dielectric function of a certain number, then you can design such a material. So our goal is to do the nanocomposite design to achieve this. So we actually had multiple interesting publications. And another interesting part is that we can transfer the material onto different devices because initially the growth really have to be on single crystal structure. And the transfer made us to succeed in the 2023 selection. The the prior two trials didn't work out. So I strongly encourage colleagues, if you are working on the MIEF project, don't give up. And if you can potentially demonstrate feasibility on your device design, then there's a possibility you can win the DMIEF. But anyway, I will stop here. And Ali.
Thank you.
Can you hear me in the back? Yeah, so maybe we can go without.
Actually, you need this to record.
Oh, okay.
Yeah. Thank you.
All right, well, thanks, Ron, for a terrific presentation and for kindly inviting us to share some of what we're doing with everyone here. So I'll be very brief, but I want to share our overall approach. And I'm scared about this thing now. Our overall approach for autonomous research and autonomous discovery of materials that combines experiments, physics-based simulations, and machine learning. And so the idea is you start with data. Ron mentioned how important data is for MGI. So you start with what you know and use machine learning to model the quantity of interest that you want to optimize. And these models are actually very computationally efficient. So what you can do then is go through every single possible material that you can synthesize, every single possible experiment that you can run, and have the machine learning model predict what the performance of that design would be and its confidence on that prediction. So it's important to have those two. It's important to have uncertainty quantification. And then, based on that, you select the material or the experiment that's going to maximize your information gain. Okay? And that's this step here. You go carry out the experiment or go to the lab and do a simulation, and either you're done and you move on to the next step, to deployment, or you add the data back into your repository and iterate. So your model, this next time around, is going to get better because it's gaining data in areas where it's not very certain about the performance, or it thinks that the performance would actually be very good. So very quickly, our application is different. This is a very general approach for optimization. It's called active learning. Our application is a new class of materials called high entropy alloys. High entropy because you take a bunch of elements and you combine them more or less equiatomically. And our goal is to develop materials for high temperature applications. So we care about two properties for high temperature applications. We care about high strength at high temperatures, but also oxidation resistance. And just like Hayen was showing you a target space, this is the mass uptake, so we want this property to be very low, and this is the strength, we want this to be very high, and you can see that there's a hole here, right? There's a space where we currently have no materials that operate at high temperatures with the appropriate oxidation resistance. So that is the goal, is to fill that gap in materials properties. So let me very briefly show you what we've done. And so, as I said, you start with the data that you have. And one of the problems is we have about 300 known materials that have been tested. So that's our database to begin with. And we were fortunate that the Air Force had collected the data for us. In many other projects, we spend months collecting the data from the literature because we don't make our results available in a way that are easily machine actionable. But we had the data, 300. Our design space was 65,000 alloys, okay? We can run, at best, 5 per week. Okay, so if you're a grad student, you don't want to explore that space brute force. 5 per week, you have 65,000 to go. What we did is, first of all, using physics-based simulations, we were able to reduce that space down to 5,000, from 65,000 to 5,000, just using computational thermodynamics, alloys that had the right crystal structure and that were single phase. Okay, that's called CALPHA. That's the technique that was used to design those alloys by Questec. And then we did physics-based simulations, and then machine learning with these 300 data points that we had, and then go to the lab and run the experiments. And it's important to understand, you actually delegate the decision-making to the system. The professor is not deciding what alloy to do next. It's the AI that's deciding what the system will do next. We did it 5 per week, and in about 5 iterations, about 23, 24 actual alloys, we found the hardest aluminum-containing high-entropy alloy ever recorded. And so this is our alloy. This is what existed in the literature that's comparable to our alloy. Okay, aluminum-containing, that's for oxidation resistance. 40% higher accuracy, higher strength, higher hardness than the current best, and very comparable to if you compare every alloy that's out there in the world. Okay, I would like to say this is a collaboration with Professor Bilionis from mechanical engineering, Mike Titus and Ken Sandage from material science, and Saswat, who's here, did a lot of the work that I'm presenting. And the approach is very general. Okay, we've used this very similar approach, driving simulations, ab initio simulations, to find materials that undergo pressure-induced phase transitions. And we very quickly found tens of new materials that under pressure change phases, which is very exciting because doing those experiments is very intensive in time and resources. And with that, I'll stop so we can have a discussion. Thank you very much. Thank you.
I'll take the microphone.
Oh, yeah. I don't want to take that.
Yeah, okay. No, it's right there. Yep, got it. I just want to end by telling you that I have included in the presentation, if you're interested, this is the MGI strategic plan from 2021, the most recent of their documents. It puts in perspective all of the things we've talked about on a very high level. This is the DEMREF report that I mentioned chairing. And finally, this is an issue of the Bridge, the National Academy of Engineering quarterly called The Bridge, which I edited. And it was published just about a month ago. And the reason I mention it is, first of all, it includes a lot of information. You'll see that Jim Warren, who is from NIST, is included among the authors. But the reason I really wanted to mention this is that as part of the activity of The Bridge, I've been interviewing engineers who do unusual things. And this is a long story, but to make this a short story, I interviewed a writer named Andy Weir in this issue. He is the writer of a book called The Martian, which was made into a movie. And I thought, this is an incredible coincidence. Here we are talking about Neil Armstrong and astronauts, and here's an issue of The Bridge in which we interviewed the author of The Martian. What an interesting coincidence that is, I thought. Anyway, just want to leave you with one final word, and that is that I think MGI and DEMREF collectively are changing the face of material science and engineering education. And they're doing it in such a way that it produces new materials fast, less expensively than we have in the past, all with the objective of deploying them to meet national priorities and social needs. And I don't think it could get any better than that, frankly. We have a long way to go. They're still making progress. There's still a lot to be achieved. But I know it's been a success to this point, and I can only imagine it getting more successful. So I will stop at that point. We can take questions if you can wait to get your cookies and whatever. But I think we should have a few questions before we break for our reception. So thank you very much. But it was so convincing that there are no questions, or the cookies are more interesting. Okay, yeah.
So how do different NSF institutes actually work?
Hold on.
Cost, yeah. I'm Ronald. So thanks for the wonderful presentation. different NSF institutes work? Is it basically a couple of professors who have been given grants on a particular area of research, and if people want to have some idea or want to get some guidance from any of them, how do they approach that?
How do they get some guidance to work together, you mean?
So is it basically NSF institutes is basically for professors? I mean, most of them seems to be professors from
The
various
PIs, the PIs are professors, yes.
PIs and professors.
Yeah.
And they seem to be already be working on some of these areas, right?
Yeah.
So is it just a continuation of their original research, or is it that they mix because they're all at different geographic locations? So how do the students work on this?
Well, remember, the key is that we're looking for new materials. So it can't be, they may be using similar approaches. I mentioned the guys at MIT who worked on the cathodes for lithium-ion batteries. You know, there were no lithium-ion batteries on the market at that place, but they were interested in it. It has to be some new technology that in terms of designing an engineering system to meet that new technology, you need new materials. So that has to be new materials for new application.
But how does the pairing work? So do all professors have to agree on a certain line of research, or do all of them work on their own and they just...
Well, no, there has to be, you know, in order for this to really work, there has to be a very close coordination. So, but I'm sure that if you looked at, last year, DEMREF, I think they awarded 73 contracts. No, I'm sorry, 37 contracts, $73 million, about $2 million each. And I'm sure there's a wide variation in how these faculty interact with one another. But the end point has to be new material, and it has to be deployable. That's the goal. Yeah, thanks. I thought I saw another hand. Yeah.
So in your vision of making and exploring new materials, do you also consider how easily deployable they would be in terms of manufacturing and in terms of distribution?
Well, I mean, you know, if you're at a university, you're not likely to be in a position to manufacture.
Right.
You can develop manufacturing technologies, but eventually you have to find a way to get it into the marketplace. And that does require some interaction with a corporate entity, typically. This is something that you folks do here now. This is not a new experience. You know, when I walk through your labs and talk to your faculty members and your students, this is something you folks have at a T. You know how to interact with industry. This adds another dimension to it. Someone comes to you and says, we want to develop a material, a new engineering system. It requires materials that don't exist today. We want to get it into the market to serve a useful purpose. That's the origin of all of this. Yeah.
You just talked about serving a useful purpose.
I'm sorry.
You just talked about serving a useful purpose with the materials that you're making, but then also taking them to market. So how do you balance the profit and the company having a moat on what they've created versus the usefulness?
Now that's a really good question. You know, I have to say that I mentioned earlier today that when I watched Neil Armstrong step off the lunar module and walk on the moon, I felt an enormous sense of pride in being an engineer. There are times today when I don't feel that. And frankly, it's because I look at some of the engineering systems that are being delivered to the marketplace without controls and which are dangerous. I look at, for example, let us take the internet and the World Wide Web as an example. They both serve useful purposes. The World Wide Web is supposed to be a platform for information. It could be available to anybody. Instead, it's morphed into a platform for disinformation. And I was reading recently about the evolution of deepfake videos. Do we really need deepfake videos to go along with fake information? That's technology that there's a profit motive, but I'm not sure it serves a useful social purpose, and that worries me a lot. So I think your question bears on something that engineers need to think much more become much more thoughtful about. Well, maybe I've said enough. Maybe we should have a longer conversation about that at some point. I'm getting too political, maybe too philosophical, but I do worry about it. I really do. Yeah.
So I kind of get the vibe that MGI on the computational aspect, it's based heavily on principal calculation, the first principle calculation, like DFT and I'm assuming MD.
Yeah.
Let's say if I want to make a material like reinforced composites, which these like depend heavily on the way that the microstructure is
Yeah.
reinforced and the way they're distributed in the matrix. So these depend like way larger scale models, like E-shell inclusion models and stuff like that. Is there a way, do you think like in the future MGI somehow will lean towards like scale models, like mega scale models?
There are many steps involved. You first of all have to develop a fundamental theoretical base. For example, in the case of semiconductor photoelectrodes, you use density functional theory. That's a good starting point for electronic properties of materials. You're talking about mechanical properties. You're talking about a composite that requires the weaving of the fibers and all. That would require a model. You'd have to have a good model in order to begin that exercise. So once you develop a model, then you could start asking, what fiber should I use? What should I use as the matrix? How should they be aligned? And you use this combinatorial synthesis approach to generate a whole host of candidate materials which go into this library. And then you have to experimentally whittle that down to a few that you can test in a lab.
So
But
MGI is specific to semiconductor?
No. It's all classes of materials. Metals, ceramics, polymers, semiconductors, the whole range of materials. It's supposed to be that broad, and it is. You're asking a question that requires a mechanical model that would be the crux of this, I think. You've got to decide how you want these fibers to interact with one, how they want to line up, how they want to be aligned in space, right?
Yeah, and I do remember like seeing something like the use of these composites in the electrical field, like the way the electric conductance is delivered differently in composites, and the way the heat transfer is also being conducted through them, etc. So it's not only like just mechanical properties; it's other things as well.
Well, it can be. I would recommend that you take a look at if you can. You'll get a copy, I think, eventually of this presentation, and you look at the strategic plan for MGI from 2021, because it's got a lot of direction, and I think that'll help you answer some of your questions. There are a lot of vignettes in which things like what you're describing are illustrated. So I think that'll help. Yes.
Thanks a lot for your presentation. It was quite insightful. So I felt that I got the vibe that the MGI is kind of, as you mentioned, focusing more and more on deployment, right? So but where does fundamental discovery come in here? Because of course that's a very important part of it. So, but it can't take a back seat. So how would you gauge that's going to evolve?
Well, let me make sure I got all of the details there, because I didn't quite follow everything you said. So let's try that again.
Oh, sure, yeah. So I was saying that from what you mentioned, it seems obviously that deployment and applications are becoming more and more important.
Right.
But it almost feels like fundamental discovery might take a backseat. Like, that's not emphasized a lot.
That's
How
where
does
it's.
that fit in?
Remember this? I showed an illustration of something called a technology readiness diagram, level diagram. The fundamental science is what you build on. You can develop models. For example, we mentioned density functional theory. It's often used in material science for various purposes, particularly for electronic materials. But you use that as your model. And then you have to ask questions about how do you go from that model to discovery. And then you ask, how do I begin to qualify that material? But you won't get in your lab to the eventual deployment unless you have a collaborator who's in industry. But MGI encompasses that whole spectrum, from the early stages of discovery all the way to deployment. And unless you can meet that objective, then it's not going to serve the interest of MGI. That's the whole objective.
I think Ron will be around during the reception.
Yeah, it's time. Now it's time for cookies and some drinks.
Keep
Yeah.
going.
I want to thank you all for being very patient and attentive. Thank you. Thank you. Yeah.